If you have stop it. Okay. Interrupt 1. Interrupt 1 is a single step interrupt. It's a single step interrupt. That means when interrupt 1 is executed, your execution will go to the single step. Okay. Now here the trap flag has to be set. If the trap flag is set, 8086 will do a type 1 interrupt after every instruction is executed. See, how do you make a trap flag to be 1? This is a flag register. Okay, you can see this is your trap flag. This is your trap flag. Okay, this trap flag, okay, this is for single step. You have to make this trap flag as 1. How do you make it? See here. First, push entire flag content to the stack. Okay, so when you push entire flag content to the stack, it comes like this. Suppose your stack pointer is 3000. Okay, before this stack pointer is pointing to 3000. Moment you do push F, you know that stack pointer will be decremented by 2, right? And it will put the flag content in the stack. This is your stack. This is your stack. Okay, this is the flag content. You can see that the flag is pushed to the stack. Okay, next push AX. What is this AX register? Push AX. Moment you do push AX, what will happen in the stack? This AX will be stored next to the stack. Yes or no? Your stack pointer will be decremented by once again 2, and then your A will be stored here and AH will be stored here. See, this is from push F. This is from push AX. So whatever result are there in AX, it will be pushed to the stack. This is your stack now. Right? See here. After that, you move the content of the stack pointer to base pointer. So what is stack pointer now? Stack pointer is pointing to the here. Yes or no? Stack pointer is pointing here. Now, okay. Now this is now copy to the base pointer. See, move stack pointer to base pointer. Next, move base pointer plus 2 AX register. Can you tell me? This is your base pointer now, right? Plus 2 means where it will go? It will come here. So base pointer plus 2 will be moved to AX. Can you tell me what will be the content of AX register here? Come on, tell me. It is flag register, right? See, your address is pointing to this value. That means, see, move AX comma base pointer plus 2. Move AX comma base pointer plus 2. So what is base pointer? Base pointer is this one, right? What is plus 2 is this one. This is content of that will be moved to AX. Can you tell me now what is there in AX register? Flag register. Sir, right? It is pointing here. BP plus 2 is pointing here. So AX will be having flag register. Now, you have to make this, see, this is now already going to AX register. This is already going to AX register now. How do you make this particular bit? How do you make this particular bit to be 1? Even though that particular bit is 0, how do you make that particular bit is 1? You just have to OR that entire register with this value, yes or no? Can you see here? You have to OR the entire content of AX register with this value. That means you put 1. Which is this position? See, you just have to OR it with 0, 0, 0, 0, 0, 0, 0, 0, 1 here, 0, 0, 0, 0, 0, 0, 0. you OR the content of the AX register, okay, that is the flag content with 0 0 0 0 0 0 1 0 0 0. So what will happen at that time? Tell me. What happens? Come on. What happens at that time? What happens with this OR? See, this particular bit, even though this bit is not 1 in AX register, that will become 1. Right? Ultimately, what is there in AX register now? Content of the flag register from above these 3 instructions. Right? So, what will happen to the content of the flag register after this OR operation? The trap bit will become 1. It will set. Okay, so now AX register is having the content of the flag register with trap flag made as 1. Okay, now what's the next work? Put it back to flag register. It is the AX register now. Put it back to flag register. Put it back to flag register. How do you put it back to flag register? How do you put it back to flag register now? Same thing. From AX, you put it back here in the stack. You put it back in the stack. How you do it? See, move AX comma BP plus 2. Can you see here? Move AX comma BP plus 2. What is BP plus 2? BP plus 2 is this one only, right? This one only. You move it back to BP plus 2. What you do? You have changed the AX register, which is the flag register content, by making trap flag to be 1. After that, put it back here. Put it back here. Right? Now, what do you do afterwards? Pop AX. Right? Pop AX. So what it will do? It will pop the content of stack pointer. Which is the stack pointer now? Tell me. Stack pointer is pointing here, right? This is stack pointer. So stack pointer, whatever data which is there in the AX register, it will go back to once again to AX register from the stack, and then comes this. Okay? Have understood this? Then comes pop F. When you do pop F, what will happen? This particular whatever content here, because when you pop, your stack pointer will be incremented by 1, right? 2. Yes or no? Right? When you push, your stack pointer will be decremented by 2. That means when you do this pop F, this flag content, okay, this flag content which is changed because of these operations will be put back into the flag register. I've understood this. Okay, that means this entire program which you have here, this entire program just sets the trap flag. Okay, so purpose of this entire program is to set trap flag. Right? Can you tell me, is there any other way to set the trap flag? Come on, tell me. Why this exercise is done? Why such a big program just to set the trap flag? Because there is no instruction we have, right? Do we have an instruction directly set the trap flag? Of course, you have some instruction to set direction flag, right? Clear flag, clear carry. But you don't have anything, right? And same time, you should not disturb the flag register. That's what we do. First, put this into the stack. Put the existing flag register content, entire flag register content into the stack. Okay, so when you put the stack, I'm explaining you this once again. When you put it in the stack, suppose the stack pointer is 3000, it will be decremented by 2, right? And then you will have this flag register. This is lower flag register, upper flag register stored in this. Have you understood this? Okay, say 3000 decremented by 2, how much? 2FFE, right? Okay, now you have put this entire flag register content into the stack. Now it is available in the stack. Copy of that is available in the stack register now. Stack memory, sorry, stack memory. After that, I want to use some register, right? I want to do some alteration, right? Now I want to use a register. Assume that AX register I am going to use. But I don't want to spoil the content of AX register. For that, what I will do? I will push the AX content also. So whatever is available in AX content will be available after that. Can you see here? Once again, push AX will decrement the stack pointer by 2 times and it will put the content of AX register. Right, now I can play with the AX register. Why? I can play with the AX register. Why? Because my data is safe here in the stack. So I will use AX register as my wish. So what I will do? I will copy the stack pointer to base pointer first. I'll copy the stack pointer to base pointer first. Okay? Because I need to put the content of the flag in the AX register now. If I want to put the content of the flag register in AX register, I have to reach here, yes or no? Yes or no? Your stack is pointing here. Right? If I want to take the content, take this content, put it in AX register, how will you do? So you add 2 to this, right? You're pointing here. First you put it in base pointer, okay? Put this address in base pointer. So base pointer plus 2 is what? The place where you have the flag content. I understood this. Okay. Now you see here. I'm going to put this BP plus 2 into AX register. Right? Now you can see at this point, you have the flag register content in AX register. And now you can play with that, yes or no? Your AX register is having flag register content, you play. You want to change whatever bit you want to do it. Right? Now what is required here is to make trap bit, the trap flag to be 1. Right? So now your trap flag position is this one, right? This is the trap flag position. So this you just have to OR this, okay? OR the content of flag register with all 0, 0, 0, 0, 0, 0, 0 with that. So what will happen at that time? Tell me. Trap flag will be set. Trap flag will be set. Yes or no? All will remain same, right? All other bits will remain same, okay, but same time trap flag will be set. Have you understood this? Okay. Now, once the trap flag is set, your AX register is having a flag register content with trap flag set. Now, can I keep it there in AX register? No, right? Where I should take it? I should take it back to flag register. So how will you do that? Once again, you just have to put the AX content into the same memory location. See here, this is pointing to a stack. You put the content of flag register, which is in AX register, into BP plus 2. Where is BP plus 2 here? This is BP plus 2, right? So you are putting it back into the flag stack. You are putting it into the stack only, right? You are not putting it back into flag register. You are putting it into the stack only, right? You are replacing this earlier flag content with a content with a trap flag set. Okay. Now that is done. That is done here. That is done here. Okay. Now your stack pointer is still pointing here. Your stack pointer is still pointing here. Right? Now you do pop AX. Because your AX is safe here. The content, the earlier content of AX is safe here. So now that data you put it back into the AX register. What you do? Next you do pop AX. When you do pop AX, it will take this content, put it back into the AX register. After that you do pop F. What it does? What pop F does? See, you have pop AX here. After that you are what it will do? It will just increment the content of the stack pointer, yes or no? Right? So what it will do? Your stack pointer will point to this. Right? When you execute pop F, stack pointer will be incremented in this, and this content will go and sit where? This content will go and sit in flag register back. Right? This is the way you can just set the trap flag. I understood this. Okay. Suppose if I want to reset the trap flag, what I should do? I want to reset the trap flag. What changes I have to do here? Just if you understand this, you can answer my question. And with 0 and everything. Is it 1 with 0? If you add 0, everything will become 0, right?
So everything else 1 and
exactly. Good. Very good. So if you want to reset trap flag, you make everything 1, 1, 1, 1, 1. Make this as 0, and this will be very good. This is what I wanted. At least 3, 4 you understand. It's very easy. It's not difficult. Okay. In question, in examination, we have asked this question. Instead of said a small change, we asked in the examination that if you want to reset it, how will you do it? Right? Maybe like only 2 students have done it. Remaining entire people sitting to they copied the same program, and this is done in open book test. Right? Okay. This is what about interrupt 1. Okay. Now, still we have more interrupts now. Interrupt 2. What the interrupt 2 does? Interrupt 2 is nothing but non-maskable interrupt. See, interrupt 2 is nothing but non-maskable interrupt. This is a software interrupt, which is a non-maskable interrupt. I told you about non-maskable interrupt. See, when 8086 receives low to high, transition to NMI input. Right? There is a separate non-maskable interrupt pin in your 8086 microprocessor, which I had told you in my previous class. Right? Okay. So now, when it receives a high signal, okay, type 2 interrupt responses, it cannot be disabled, it cannot be masked by any program or instruction. Right? So the interrupt number 2 is for non-maskable interrupt. Okay. Now this interrupt cannot be masked. You have to obey this interrupt whenever a service is requested through non-maskable interrupt pin, that is interrupt number 2, then whatever interrupt service routine corresponding to that interrupt 2 has to be obeyed, has to be executed. Okay, let us go to interrupt number 3. Interrupt number 3 is a breakpoint. What is breakpoint? All of you use the breakpoint, right? Interrupt is for breakpoint. In C programming, you are done breakpoint. Alright? So what is breakpoint? Tell me. What is breakpoint? You can just put a break for your execution, right? A point, it will just execute till that point and then it will stop. It's the breakpoint. Okay? I understood this. Okay. Now, for that, you have an interrupt which is called interrupt 3. That breakpoint can be activated through interrupt number 3 to implement breakpoint routines. The system executes instruction up to the breakpoint and then goes into the breakpoint routine. Okay, and also it is called as debugging. So interrupt number 3 is for that. Okay, and let us go interrupt number 4. Okay, overflow. Right, like divide by 0. Interrupt number 0 is divided by 0, right? Overflow is also another catastrophic condition of a microprocessor. Yes or no? Right? So whenever there is an overflow in operation, it has to give an error. It has to, microprocessor has to be informed, okay, or maybe user has to be informed there is an overflow. At that time, you have interrupt overflow, interrupt 4. Interrupt 4 is for overflow. Okay? Then you have, see, suppose if there is no overflow, okay, so then there will be no operation, no operation instruction. See, for example, only place where you will not get overflow is no instruction. Do you know this NOP is also instruction? No operation. What is the meaning of no operation for microprocessor? Right? It's quite very familiar. Do nothing. Right? Runs a better. No operation. Just for now. Okay? You should know the meaning of all those things, right? That's what we do. So these are the, I told you the top 5 interrupt numbers are actually are reserved for specific purposes, right? So now, how many interrupts are left now for us? Out of 256, we saw only top 5, top 6, right? Top 5, that's all. What about remaining? In that, have you just checked in my previous slide that certain interrupts from 5 to 32 is reserved by the Intel? It is reserved by the Intel. Right? I don't know why it is reserved. Okay. Now, above that, after 32 interrupts, you can use it for different purpose. Right? Out of that, one you have already used. Certain interrupts you have already used in the lab. Right? What is that? 21 you have used. Anything else you use? Did you generate a clock? Right? You have used some interrupt for file operation. Yes or no? All those interrupts are from that above 32 to 256. Okay. Of course, it is very difficult to remember all these numbers. You need not remember all the things. Okay. That's very. Need not buy it this. I already told you about interrupt signal. Interrupt signal of your microprocessor. Right? There is an interrupt signal. What is interrupt signal? It allows external signal to interrupt the execution of the microprocessor. This is called hardware interrupt, not software interrupt. Okay. So this interrupt can be masked, can be disabled. Okay. So how can we disable interrupt? Okay. See here, interrupt flag. In flag register there is a flag called as interrupt flag. Okay. So whenever microprocessor is actually it is interrupted through interrupt signal, that's high signal on the interrupt pin, right? Then your interrupt flag will be set automatically. So moment you detect one interrupt flag, you can, if you don't want to obey that interrupt, if you don't want to give any acknowledgement for that interrupt, you execute an instruction clear interrupt flag. It will clear interrupt flag. I've understood this, right? Okay. So in that way you can disable it. If you want to enable it once again, there's one more instruction, set interrupt flag. You have seen clear carry, right? Clear carry, set carry, clear carry. What it does, it sets a carry flag and clears the carry flag. Like that, this interrupt flag also can be cleared or set. But you don't have this for the trap flag. So whenever you want to set or reset trap flag, you have to use that program which you have just seen before this. Have you understood now? Fine? Okay. So now see 8086 will reset when interrupt flag becomes 0. Okay. Now also 8086 will branch to interrupt service routine when IF becomes 0. Okay. And it will become 1 when it returns from the interrupt service routine. See, what is this? I will tell you. See, moment interrupt pin is activated, okay, interrupt pin is activated, your interrupt IF flag, interrupt flag will become 1, right? Okay. Next, if you want to really acknowledge, okay, the interrupt, okay, you will not use any clear interrupt flag. It will go to interrupt service routine. It will go to interrupt service routine. Have you understood this? Okay. It will execute interrupt service routine. Whatever you have written in interrupt service routine. Okay. Now, what happens? This interrupt service routine is like a subroutine. It has got an instruction called IRET. IRET. Okay. See, when it goes to interrupt service routine, it will set the interrupt flag to 0. Okay, it will set the interrupt flag to 0. Now when it comes out, it will make interrupt flag to 1 once again. I understood this. Okay, so and after that it will set the interrupt flag to 0 once again. Why? Because if the interrupt flag is not 0, it is not giving opportunity for another interrupt signal. That's why interrupt flag will be set to 0 once again. I have understood this. Okay, so this is what actually done by interrupt signal. This all I think enough for you to know about interrupt signal. Vectoring of interrupt. What is vectoring of interrupt? This is very important. Okay. You know that your interrupt having vector number from 0 to 255, right? Okay, 0 to 255. Okay. Now, whenever an interrupt signal goes to the interrupt pin, okay, that means microprocessor is interrupted. Who has interrupted? How does microprocessor come to know who has interrupted? Tell me. It will come to know the who has interrupted by using vector number. By using vector number. That means whenever microprocessor is interrupted, microprocessor should also get this interrupt number on the data line. That's also required. From where microprocessor gets the data? From data line only, right? So simultaneously you have to supply the data to the microprocessor to data line. That means you have to generate an interrupt vector whenever you interrupt a microprocessor. For that you need a hardware, yes or no? Don't you think you need a hardware? Right. See, you have this microprocessor. This is the microprocessor, and this is the interrupt pin. You are given high here. That means your interrupt flag will become 1. That means you want microprocessor to be interrupted. How does microprocessor come to know who has interrupted? That depends on the data you put in the data line. Your D0 to D7, whatever data which is available whenever it's interrupted, that is going to be the vector number. Okay, that vector number has to be generated simultaneously with the interrupt signal. For that we need a circuit. Right, that's what we are going to see in the next slide. Okay, how does it generates a vector number? Next. See here. Can you see the circuit? What is this 75LS244? Tell me. You already used it. Ah. What is this? Okay, what is 75LS244? See this is a buffer, right? We already studied this in your pins and signals. The buffer. Whenever this chip is activated, whatever input you given, it will come here. Yes or no? Yes or no? Come on. This is a buffer. Whenever this chip is activated, can you tell me when the chip will be activated? Come on. When this chip will be activated? When you give 0 0 here, yes or no? Yes or no? When you give 0 0 here, this chip will be activated. And whatever data you give here, it will come here. Can you tell me what is this? These are all called as dip switch. These are the switches. When it is up, okay, it will give 0. When it is down, it will give 1. See, this switch up down switch. Now when it is up, it gives 0. When it is down, it will give 1. So this dip switch is going to give you the 0 and 1s. So accordingly, you will get the values here. Yes or no? And when this particular chip is selected by giving 00 here, whatever data you have here, it will come here. Have understood this? Right? So now this data is connected to the data line. Have understood this? Okay. Now this is connected to interrupt acknowledgement. Now you see here, listen carefully, understand how this is going to generate the data when the interrupt is actually activated. Now listen, assume that your microprocessor has been given interrupt. Your microprocessor has been given interrupt. The signal at interrupt is going high. Now assume that microprocessor has generated interrupt acknowledgement. That means it is actually ready to serve that interrupt. That means it is actually giving low into interrupt acknowledgement signal. So interrupt acknowledgement signal is coming to be low here, 0, and that is connected to the chip select, yes or no? And when this chip is selected, see, whatever the vector number you set in this dip switch is available in the data line. Can you see here? It's available in the data line. I have understood this. This is the way you can just generate a vector number. Okay? Generate a vector number, interrupt vector number. Moment interrupt signal is given to the microprocessor. See, this is the circuit you need to use. This is one of the circuit which is used. Okay, so I have explained you how does it work. When the microprocessor is getting interrupt signal, high signal, it will generate interrupt acknowledgement signal which is low, active low. Right, which is active low. Definitely when it gets active low, this chip will get activated. Okay, and definitely whatever data available here will be available in your data line D0 to D7. Microprocessor will take the data. Right? So when interrupt is not there, when the interrupt is not applied to microprocessor, does this chip get activated? No, because interrupt acknowledgement will 1. So this will be getting 1 means this chip is not got activated. So have you understood now? So whenever microprocessor is being interrupted by giving high signal to interrupt, how the interrupt vector is generated? This is the circuit. Right? Okay. So now see this one. What if this is an alternative to that? Right? In the previous circuit, you have this switch which is giving you various values. Instead of that, you can have this one NAND gate. Okay, you can have this NAND gate, and you can have this 7 interrupt request. That means there are 7 lines which is requesting the interrupt to the microprocessor. Fine. Okay. Now see, whichever request want to interrupt microprocessor, it will send 0. Okay. It will send 0 to this NAND gate, right? And other interrupts which does not want to send any interrupts will have 1 in that. Assume that interrupt 7 want to send an interrupt request. So this will put 0 here, and all other things will become 1, 1, 1, 1, 1. Have understood this? Right? Which will give you a signal 1 here. Yes or no? Come on. That means your interrupt pin, this is interrupt pin, this is INTR pin of the microprocessor is activated. Yes or no? Definitely, it will give you a zero signal in the interrupt acknowledgement. Right? That will generate, that will activate this chip. That will activate this chip. Now tell me what happens? What happens? What data will be going into the microprocessor? You will get, see, this is connected here. You will get 0, 1, 1, 1. You will get 0, 1, 1, 1, 1, 1, 1, 1. Going inside the microprocessor. What does microprocessor will come to know with this arrangement? It will come to know that this particular interrupt request 0, interrupt request 7 is 7 wanted to interrupt and execute its corresponding interrupt service routine. Right? Now, same thing for other interrupt, yes or no? Suppose interrupt request 0 want to interrupt microprocessor, it will put 0. Yes or no? It will put 0 in this. Other interrupts doesn't want to interrupt. You have 1, 1, 1, 1, 1, 1, 1 in this. Once again, you will get 1 here. Interrupt will be activated. Interrupt acknowledgement will become 0. Now can you tell me what data will be loaded to the data line? You get 1, 1, 1, 1, 1, 1, 0. That indicates, that tells the microprocessor that interrupt request 0 has given the request. I understood this. Say if this arrangement is not there, assume if this arrangement is not there, and you have only this to accommodate 8 interrupt requests here, right? How does the microprocessor come to know who has interrupted? Is it possible? Not possible. If this is not there, it's not possible, right? So because of this arrangement, microprocessor will get a data for every interrupt request. Right? Whenever interrupt 0 is requested, this will become 0, all will become 1. Of course, interrupt signal will go. Right? How does microprocessor comes to know that the interrupt request has gone to interrupt request 0 only from this data? Microprocessor will be getting the data 1, 1, 1, 1, 1. See, it will get 1, 1, 1, 1, 1, 1, 1, 0. With this data, microprocessor will come to know that the interrupt request is from interrupt request 0 only. There is one drawback in this. What is the drawback? It is possible to accommodate 8 interrupt requests. It is possible to accommodate 8 interrupt requests. Can 2 people interrupt at a time? Can? It's not possible. Right. So how does it resolve actually? Suppose assume that interrupt 0 also sending 0, interrupt 7 also sending 0. There are 2 interrupt requests is going in this. Yes or no? Of course, this is going to be 1 here. Not a problem. You are getting different data. Microprocessor will come to know that these 2 people have given interrupt. But how does it serve that interrupt request? At that time, it has to do what we call it as priority. Yes or no? Right? If 2 of you come to me at a time asking for something, can I serve both of you at a time? No. So I should give priority. I understood this. It's called priority. So according to that, you have to redesign the circuit to include what you call it as priority encoder. Have you used priority encoder in your DD? We're not going to study here now, but we can use a priority encoder and you can give priority to that. I've understood this. Okay. So at present, this setup can serve only one interrupt request. There's no setup to give priority here. I understood it. Okay. So this is the circuit which is used to load the which interrupt has actually interrupted the microprocessor. I've understood this circuit now. The circuit is very important. You will be asked to design the same circuit for different interrupt vector number. We'll see that in this thing. See. Now see here. What is the interrupt vector going inside based on interrupt request? See, when your interrupt request 0 is becoming 0, that means your in IRQ0 want to interrupt microprocessor. That means assume that this is nothing but your temperature sensor. This is nothing but your temperature sensor. So IRQ0 is a temperature sensor. IRQ1, maybe it is a humidity sensor. IRQ2, okay, maybe a rain sensor, okay. IRQ3, maybe pressure sensor. These are all the sensors which are connected. Assume all these are connected. Now, whenever temperature sensor wants to send the data to microprocessor, okay, microprocessor has to be interrupted, right? Microprocessor has to be known. So, as usual, what it will do? It will put 0. It will put 0 here. It will put 0 here. Right? It put 0 here. Definitely 1 will come here. Your interrupt signal will be 1. Right? Microprocessor is interrupted very well. Definitely it will give interrupt acknowledgement signal, and this will be activated. Which number will go inside the data bus now? That is this number FEH will go to. That means what is the vector number for that interrupt for the temperature sensor? FEH. Similarly, what is the interrupt number for the humidity sensor? FDH. That means microprocessor will come to know that it is receiving temperature data. Accordingly, in this vector table, okay, you need to have a program which reads the temperature data and displays the temperature data. I've understood this. Okay. Similarly, whenever humidity sensor wants to send the data, this will generate 0 in this. Then what is the number which is placed on the data bus? It is FDH and so on. I have understood this. And this is very important for any. If there is only one interrupt available in this world, okay. You don't need this number. But there are multiple data, multiple sensors connected to the microprocessor. Multiple people want to communicate the data, right? And I have told you that this particular arrangement can serve only one interrupt at a time, because this does not have that encoder, priority encoder, right? Suppose, as I told you, that both temperature and humidity sensor wants to send the data, right? But those two are separate sensors. It has to go through separate requests, right? So, of course, microprocessor will be interrupted, circuits are interrupted, right? But the data which is going is something different than what is specified in this, yes or no? So, that is a drawback in this. That is a drawback in this particular circuit, right? Then, for this, the solution to this is called as programmable interrupt controller. There's something called programmable interrupt controller. I don't know whether we will be getting a chance to study that or not because of the time constraints. There's something called programmable interrupt controller, which will actually give a priority. Where we set the priority, that means whenever both the interrupts are trying to send 0, then set a priority. Right? Suppose if you set a priority for temperature, temperature will be accepted first and then humidity will be accepted first. That is programmable. It is left to you. I understood this. Okay, in programmable interrupt controller. Okay, is the circuit. So we have already seen this, right? These are top priority interrupts. See, out of all the interrupts we have seen, these are the top priority interrupt, that is divided by 0. See, high priority is for this, divided by 0, interrupt, the small interrupts, okay, and then interrupt overflow, non-maskable interrupt, and then interrupt and this single step. This is for 8086. This is a fixed priority which is actually, have understood this. Okay, first priority is for divide by 0, interrupt number with interrupt number, interrupt overflow. Then next priority for non-maskable, then priority for interrupt signal, then the single step. Single step, you know which interrupt number is. Okay, you all know about it. We already discussed that. Okay, the high priority to low priority. Okay, just see this. What happens when the microprocessor receives an interrupt? Just check that. So just answer the number. Just go through that, whatever is there on the. I already told you about this. Just it's written in the form of some slides.